All right, good morning, everyone. Um, Something that would be good to take a look at um, is there is a big kind of rundown of what to expect for the rest of the semester that was posted um, on Canvas. So that has kind of what to expect as far as exams and the final and for class this week. Um, so make sure to look at that. And if you have any questions um, about anything that is there, or if you feel like there is anything that isn't, um, let me know. But it is definitely exciting to almost be done with this difficult semester. Okay. So let's get going. So, what we've been talking about for, um, I guess, the last few classes is power series. So, a power series centered at A is a series where you have some coefficients. So, you have parts of the series which depend on n, but then you can also have a variable x, which appears as x minus a raised to the nth power. So this, if you were to write out the terms, this would look like an infinite polynomial. It would have a c0 term and then c1 times x minus a plus c2 times x minus a squared, and so on. So what we've seen about these power series is that the question you can ask, or the first question you can ask after they're introduced, is what x's make them converge? So if you pick a specific x, then this becomes a numerical series, and you can ask that converges or diverges. And there are really three options for that. Either it only converges at A, and that's because if you put in A, you have a zero here. So almost every term that you write out is zero, except the constant one, which doesn't have any x's in it. The other option is that this converges for all x. And the fourth option is that there's some interval on which it converges. And so this is described as having a number r called the radius of convergence. So if you take the center A, which is x minus a in the power series, if you go r in either direction, you're going to converge on that interval. If you go more than r away, so on the outsides, you're going to diverge. And at the endpoints, you can go either way. You have to explicitly check those. So this is the third kind of most complicated option. There's some finite interval which is symmetric around your center. And the distance from the center to the edge of your interval, that's the radius of convergence. So the r, this distance is called a radius. The whole interval, including whether you include the endpoints or not, that's called the interval of convergence. And so we saw examples of checking where power series converge by using either the ratio or root test and saying, depending on which x we put in, we get a different limit from the ratio or root test. And so we can use that to set up an inequality to decide when this series converges. What we also saw, this was the new idea, was that you can represent functions as power series. So if we take the standard geometric power series, x to the n, it's geometric, so it converges when the thing you are raising the power to. So this converges if the absolute value of x is less than 1. And we know that the endpoints, meaning 1 and -1, aren't included here because those don't make geometric series converge. So we know because it's geometric that it converges for x that satisfy this inequality. So this 1 is where we get the radius of 1. If you solve this inequality, that means that x is between 1 and -1. And like I said, we don't include the endpoints there because if you put 1 or -1 in, you get a divergent series. So given this series, we can analyze it and say, we know what its radius is, we know and we know the interval on which it converges. But then what we can say is on this interval, this series converges, but we know it converges to this function or this quantity here. So what we'll say is that this function, 1/1 minus x, is equal to the function defined by this power series as on this range. So on the interval -1 to 1. So what this means is that, or what really this is introducing, is a new way of talking about functions. Rather than a kind of closed formula, you can write down a power series and think of that as a function where the domain is that interval of convergence, which is the x's, which you can substitute in and actually get a number out. You know that it converges there, so it's some number, that number is the output of the function. So so we want to know, how can we represent functions as series? And one way is using this as a starting point. If you take this x here, that matches up with this x right here. So if you were to change this x to something else, you can make the corresponding change in the series, and the series you get is equal to the function that you get. And so some examples that we saw last time, 1/2 minus x looks just like this, except there's a 2x instead of an x. So if we make the corresponding change in the series, instead of 1 minus x giving us x to the n, 1 minus 2x gives us 2x to the n, which after using exponent rule becomes 2n times x to the n. And so this series represents this function, but we need to check where it actually represents it. And the key here is, just like in the original case, this converges when whatever is being raised to the n has absolute value less than 1. We get the same inequality here. Now it's 2x that we're subtracting, so it's 2x raised to the n, and 2x has to have absolute value less than 1. So by making this substitution, we get a different interval, but we still know that on this interval, this series and this function are the same. This series represents this function. And so we can make this kind of stuffing in move whenever we see 1/1 minus something. And in some cases, we have to be a little creative. 1/1 plus x squared, we can write that as 1/1 minus something, that something becomes raised to the nth power, and we can write that as a series. So this series, minus 1 to the n times x to the 2n, represents this function. We again have to check where the series and the function match up by taking what's being raised to the nth power, and that has absolute value less than 1. And killing the minus sign and taking the square root, we get that it also converges with absolute value of x less than 1. So this is one way of taking a series you know, and or taking a function that you know a series for, and using that to find a series for another function. So starting from this function and this series, if we change this, we make the corresponding change in the series. Another way that we can do this is also of kind of theoretical interest. And I made this connection last time, 1 over 1 plus x squared. The integral of this is arctangent. So a question is, how could you find a series for arctangent? And the way that we can do that is this function has this as its series. If you integrate this, you get arctangent. What we'll say is, if you integrate this series, you get the series for arctangent. So what does that exactly mean a little more carefully? So the situation is this. If you have a power series with whatever coefficients and center A, and it has a radius of convergence r greater than 0. So this r could be finite. This might just converge on a finite interval, or this r could be infinity, meaning this series converges everywhere. So this is really just ruling out the case where it only converges at its center. Then this series actually defines a function, which is what we've been talking about. It's a function of x, but this function is differentiable. And if you are differentiable, you are continuous on the interval of convergence. And not only that, but there's a formula for how you can find the series for the derivative and a series for the integral. I mentioned continuous because continuous functions have indefinite integrals, so we could ask what those are. And what the formula says is that if f of x is given by this series, then the derivative is given by the series where what it looks like is you use the power rule. In this case, you bring down if you're looking at this kind of expression, Cn is a constant. It doesn't have any x's, so it stays there. You use the power rule on here, so the n comes down. The new exponent is 1 smaller, that's n minus 1. And the inside has a derivative 1, so the chain rule doesn't do anything for you. But also, if you have a function that has this as its series, and you want to know a series for the integral, well, the integral of your function you can find by integrating the series. And so if you apply the integral power rule here, this is a constant. It doesn't have any x's, so it stays there. If you integrate this with the power rule, the exponent increases from n to n plus 1, and then you divide by the new exponent. And then there's a constant. And if you know that this series for the original function has a radius of convergence r, the series you get by differentiating and integrating also have that same radius of convergence. And they're still centered at A. One thing to watch out for is when you form these two new series, they might have different intervals of convergence. So you'd want to check the endpoints separately. So what is happening here, and the terminology that gets used to describe what's going on, is that given a function that can be represented as a series, we can differentiate and integrate term by term. Meaning, if you were to write out the original series as like an infinite polynomial, and you were to pretend that you could use the power rule on every single term, the series you end up writing down would be the series for the derivative. So for instance, and we'll go through this example a little bit later, but I want to write out this term by term stuff. So suppose you had a function whose series was 1 plus x squared plus x cubed plus x to the 4th plus so on. Okay. And we actually know the 1 over 1 minus x does have this series. What this term by term stuff is saying is that if you want to know the series for the derivative of f, all you do is take the derivative of each of these terms separately. So a series for the derivative, the 1 goes away, x becomes 1, x squared becomes 2x, x cubed becomes 3x squared, x to the 4th becomes 4x cubed, and so on. And the integral of f of x, there's going to be, so you integrate each of these. So 1 becomes x becomes x squared over 2, x squared becomes x cubed over 3, and so on, and then there's this plus c. So what those formulas were saying is if you actually wrote them out, you could differentiate just like you would like using the power rule formula, and you integrate just like using the power rule formula. Which is kind of surprising that you have a series defined by these functions, and integrating and differentiating essentially works as well as it possibly could. First, that you're able to differentiate and integrate is kind of surprising, but also that it works like write it out as a big polynomial and use the power rule a bunch. That actually works is kind of surprising. So we'll see some examples below, but questions about how kind of the general, this general fact about how integrating and differentiating series goes. Right. So we're seeing that if you actually wrote out the terms, you could integrate or differentiate each term separately. And these formulas are saying, rather than actually doing it in every term written out, we know that every term looks like this. So take the formula for what every term looks like and differentiate or integrate that formula. Another kind of surprising fact, which we won't use a lot, but is kind of putting it out there is surprising that it's true. Part of what this is saying is if you write down a power series and it converges on some interval, either a finite one or everywhere, the thing you write down is differentiable and continuous, so you can integrate it. So the way that we are mostly going to be talking about is if you have a series for a known function, then you can find a series for that function's integral or derivative. But things like 1/1 plus x squared, the fact that it is integrable and you can differentiate it is not a huge surprise. But what is surprising is if you write down any series at all, and if you can check it converges somewhere, the thing you wrote down is differentiable. So representing functions by power series, not only does it give you a lot of kind of flexibility in what series look like, but the things you come up with in this way are actually very nice functions. So let's see this in action, or using these facts here to come up with some new series that we don't have a way to find yet. So here's our question. Let's find a power series representation centered at 0 for this function. F of x is 1 minus x squared. So what we've been doing so far is if you have something that looks like 1/1 minus something, we could find a series for that. But we don't have that right now. But what we can notice is that this function is the derivative of 1/1 minus x. So if you take 1/1 minus x, you can use the quotient rule if you want. We can also write it with a negative exponent and then use the chain rule. So the chain rule to this, the -1 comes down, the exponent decreases to -2, and then the chain rule, there's a negative in front of the x here, so that gives us an extra negative there. And simplifying, these negatives cancel, rewrite this negative exponent as 1/1 minus x squared. So the function we are looking at and we want to find a series for is the derivative of 1/1 minus x. And now we can use that fact that was on the previous page. Here is a function we know a series for. If you want to find a series for the derivative, then differentiate the series. So what we're going to do is take 1/1 minus x. We know a series for that. We're going to differentiate that. And what will happen is, here's the way we can think about this. 1/1 minus x, and the series from 0 to infinity of x to the n, these are equal. So what we'll do is say if we differentiate 1, we get the function we're looking at. If we differentiate this one, then we'll get a series. And the function that we are interested in has this as its series. So that's the kind of maneuvering here. And when we come to take the derivative of this series, how we do it is saying what we get will be a new series. how we find what the terms of that power series are look at the terms of this series, these x to the n's, and apply the power rule. So the n comes down, the new exponent decreases to n minus 1. And the series that we get is the series for the derivative. And this is the example that we had up before. So what happened here is, if we write this out as an infinite polynomial, if we put in 0, we have n equals 0. So that becomes 0. If we put in 1, then we have 1 times x to the 0, which is 1. If we put in 2, we have 2 times x to the 1, which is 2x. We put in 3, that's 3 times x to the 3 minus 1, that's 3x squared, and so on. So this series gives us this expression all written out. And if we look at the original series here, this series, if we write it out, is 1 plus x squared plus x cubed plus x to the 4th. And if we took the power rule for each of these terms, this is exactly what we would get. So that's how this differentiating works. If you actually wrote it out and took the derivative, you get the right answer. But we don't need to write it out if we just use the formula here. What's also important to point out is that the original series, so that's this connection, 1 over 1 minus x, and the sum of x to the n, that correspondence, that representation worked on absolute value of x less than 1. So that was the interval of convergence for this series, and that's where this series and this function matched up. The new series we get also works on that same region. So this still works for absolute value of x less than 1. What can happen is that maybe the endpoints are different. So you might have to, you'd have to check 1 and -1 to see exactly, or to see explicitly if this series converges for those values. But on the main part of the interval, that doesn't change when you differentiate a series. What's also good to point out is, and maybe you saw this, but if not, it's not a huge thing. When we took this derivative, we got an n-1 here, which makes things look a little weird. For n equals 0, what we get is 0 times x raised to the -1. And in power series, and this is part of what makes power series so nice, is you don't have negative exponents. You also don't have fractional exponents. So for n equals 0, it looks like we have an exponent we're not allowed to. And the only reason that it works is because the coefficient n is equal to 0 in that case. And in wanting to kind of avoid that weirdness, which doesn't actually cause any problems, but you might just say, I don't really want there to be a negative exponent ever, even if the coefficient is 0. One thing we can say is that since this constant term, this 1 at the beginning, when we take its derivative at 0, we can really just say this series starting at n equals 0 is kind of redundant, because if you pick n equals 0 and put that in, you just get 0. So we might as well just start with n equals 1. So this second thing here is saying just start at n equals 1, which gives you this part of the series, which isn't changing anything because we're just losing a 0, but going from starting at 0 to 1 is really just reflecting the first term is now 0, and so we don't need to keep track of it anymore. So that's not a necessary step, but is something that sometimes happens if you're looking at maybe examples in the textbook or other places, that sort of changing the index to throw out these 0 terms is something that can be done. So like I said, what we want to keep track of is the radius of, so the center stays the same. They're both centered at 0, and the radius stays the same. The radius is 1 in both cases. But we want to talk about the endpoint. So there are kind of two things down here. I'll focus on the right part. Well, no, I did this so I'd focus on the left. So another sort of bookkeeping thing, which is not hugely important, but if it shows up and you haven't seen it before, you can have no idea what's going on. So it's good to address it here. So taking this form right here from 1 to infinity of nx to the n minus 1. What you might think is, it was kind of nice having the exponent just be the variable, a whole number, instead of this n minus 1. So we can do what's called a re-indexing. What that means is this n minus 1 here, let's replace that. We're going to call that m. So we want our exponent to just be a single number, not this n minus 1. And what happens if we try to do that? Well, then we're kind of thinking like a little U substitution-esque. We're seeing what happens to where we start and what happens to this n, which is the coefficient. So if we want to make this substitution here, call n minus 1 m, then adding 1 to both sides, just n is m plus 1. And that says that this n is going to be m plus 1. And then we also need to think about where we start. So if n equals 1, then using this equation here, if n equals 1, or rather putting n equals 1 in here, the corresponding m is 0. So what we're doing is we're going to rewrite this series starting in a different place with different looking coefficients and different looking exponents. But if you actually write out these series, you'll see that you write out exactly the same terms. The n equals 1 term here corresponds to the m equals 0 here. The n equals 2 term will correspond to m equals 1 here. And in both cases, this is the series you're going to write out. 1 plus 2x plus 3x squared plus so on. So this is a move which is not really necessary, but sometimes changing the appearance can be a move people textbooks or lecture notes will make, and so it's good to at least see these two are the same series. If you write them out, you will write out exactly the same thing, so exactly this, but they're presented differently just to give yourself an exponent which is just a a single number rather than n minus 1. So we also need to think about this indexing stuff is more cosmetic than anything. But what we do really need to check is we found this series, the series from, we'll take this version, from 1 to infinity and x to the n minus 1. This series represents this function for absolute value of x less than 1, the interval on which the original series worked. But we need to think about what happens at the endpoints. Those can change. So what happens if you put in 1 or minus 1? And if we put, say, we'll take the re-indexed version. If we put 1 or minus 1 into here, then in both cases, if we put in 1, we get m plus 1. If we put in minus 1, we get negative 1 to the m plus 1. Both of those series diverge by the test of divergence. This one just goes to infinity. This one is going to negative and positive infinity depending on if your alternating part is 1 or minus 1. So what we can say is that this function can be represented by either of these series, which give you this infinite polynomial version. The radius is 1, just like the original function was, and the interval doesn't include the endpoints, so it's 1 to negative 1. So a lot happened there, but I'd say the important takeaways, we're trying to fit a lot of different things into this example, is we know that this function and this series match up. So if we differentiate the series, that gives us the series, or that gives us the correct series for differentiating the function as a formula. And since this, so these colors, since this function and this series match up on the absolute value of x less than 1, the derivative and the differentiated series also match up on that same, with an interval with the same center and radius. The left side of this is mostly cosmetic, but one thing you really do need to check is check the endpoints. So here, looking for when x is 1 and negative 1, neither of those work, so the interval is negative 1 to 1. So are there questions I can try to clarify before we see a different example? So let's do this thing that I hinted at. Let's find a power series centered at 0 for inverse tangent. And we'll find its interval and radius of convergence along the way. So the fact that we know is inverse tangent is the integral. So this technically includes a plus c, but we'll forget about that. This is an antiderivative of 1 over 1 plus x squared. And as we saw, 1 plus 1 over x squared, we can write in the 1 over 1 minus something form. And we can find a series for that. So here what we're doing is that this function has this series. We know that because 1 over 1 minus something, take that something and substitute it into the x to the n series. So if you put what we're doing is we're taking this minus x to the n, or minus this minus x squared, and putting that raised to the nth power. And if you simplify this, you get minus 1 to the n times x to the 2n. So this was something that we did before. This function, underlined in blue, we can write in this form, and we can write that using, or that is represented by this series, which we can rewrite as this series. So that blue underlined stuff is what we did in a previous example. But what we can say is, what we are interested in is the integral of this function. So how we can find a series for the integral of 1 over 1 plus x squared, sorry, this blue stuff, it's got to go, is we can integrate this series term by term. And so you can do this, so to see what's happening, you can write out this series. So if we did that, that would look something like, so for 0, that's 1 minus x squared plus x to the 4th minus x to the 6th plus so on. So this is the series, if you wrote it out, that we have here. And what we can say is that if we integrate the function, so let me use some of the errors I had before. This function and this series are the same. So if I want to go from this function and integrate it to get this function, I can go from this series and integrate it to get that new series. And so what we're doing is actually integrating each of these terms using the power rule. We can do that by the formula by saying every term looks like this for some n. And so anything that looks like this, if we want to integrate it, the negative 1 to the n doesn't have any x's, so that stays there. X to the 2n, 2n is some exponent. That's the 2, the 4, the 6. We're saying whatever exponent that is, increase it by 1 and divide by that new exponent. So that's what happens if you integrate term by term. If you try to integrate each of these using the power rule, sorry, keep some of this stuff. Oh no, tiny arrows. Right, so if we integrate this formula, this is the expression we get. There's a plus c because integrating, there's always a plus c. So what we know is that the integral of this series, we can write, if we actually write this out, all of the terms, get x, so n equals 0, that's 1, that's 1, that's 1, so we get just x. If n is 1, we have a negative x to the 3 divided by 3. If we put in 2, we're positive again, x to the 5th divided by 5, and so on. Plus the c, which we'll write in the front. And the big point is, if you took this version and actually integrated it, each of the terms, this is exactly what you would get. The c is there because there's always a constant. 1 becomes x, negative x squared becomes negative x cubed over 3, positive x to the 4th becomes positive x to the 5th over 5, and so on. So the series for inverse tangent looks like this. But one thing we want to do here is inverse tangent is a specific antiderivative, and this is the general one. So we want to pick what this c actually is. How we do that is we know that this function equals this series for some choice of c. So pick an x, and that will give us an equation only involving c. If you put x equals 0 into inverse tangent of 0 is 0. If you put 0 into this series here, all of these terms with x's become 0, and so you only have this c left. So since these two are supposed to be equal, and the left side, you put in 0 gives you 0. If you put 0 into the right side, you get c. The c must actually be 0. So it turns out that there isn't a constant here. And a formula for inverse tangent, or a series which represents it, is the series from 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And because the original series worked on absolute value of x less than 1, and we checked that this was the case when we did this example before, this series also works for absolute value of x less than 1. But like I said before, while the radius stays the same, the endpoints can change. So that means for x equals 1 and negative 1, we need to check explicitly if this series converges. And if we do that, so if we put in 1 raised to anything is 1, so we just get the alternating series. This thing converges by the alternating series test. 1 over 2n plus 1 is decreasing, its limit is 0, so it converges. If we put in minus 1, this is what we get putting minus 1 in here. And what happens is 2n plus 1, negative 1 to the 2n is 1 because you're raising it to an even power. So there's just an extra factor of 1 of negative 1 coming from here. So we can combine that, all our negative 1s together in the top to be n plus 1. This, again, is an alternating series, and you write down literally the same two lines. So what that means is this series representation that we found also converges at the endpoints. So this series representation, inverse tangent of x, is minus 1 to the n, x to the 2n plus 1 over 2n plus 1. That series has radius 1, and its interval includes both of its endpoints, 1 and negative 1. So the last topic is Taylor series, which I won't start now. But what I do want to say is this fact gives us access to computing new sums of series. So the question we could ask is, if we look at this series, we know it converges, but we can ask, what does it converge to? And what we know is that Because this is this is the series you get if you put 1 into this power series. But the whole point of this power series represents this function. So if you put 1 into this series, it's going to converge, and what it converges to is what you get if you put 1 into this function. So this is a new way of finding sums of series. If you know that if you know a power series for some function, and you evaluate the series at a particular x, you can tell that you can figure out what the sum is by putting that x into the corresponding function. So this is a big new way of finding sums of series, by really saying, well, I know this series represents a function, so instead of thinking of it as a series, take that x and put it into the function and just see what that is. So in particular, this gives us a series which, if we multiply this series by 4, it gives you a series that sums up to pi. Okay. Then that is where we'll stop for today. On Wednesday, we'll touch on the last topic, which is, we won't really go into it, but how can you kind of build series from scratch? That's what the Taylor series is all about. There's a formula that says, given a function, here's what this series looks like. So we'll see that it has some advantages, but also some kind of disadvantages relative to the methods we've been talking about before, or today and last Friday. Okay. So if you guys have any questions, I can pull up the lecture notes and talk about those some more. If not, take a look at the big announcement that I put up on Canvas yesterday. There are several things, there are a bunch of things left for the semester, but it is all kind of spread out over time. So it will take some good time management, but I guess you have kind of take-home exams, which you can spread out to fit around other things in your schedule.